So welcome to the session of GroupBy. Gavin Campbell will be talking about effective unit testing for SQL Server. You can take it away, Gavin.
Okay, cool. Are you seeing effective unit testing for SQL Server on the screen?
We are. I was going to make a joke about seeing something for Oracle, but no. Yes,
there we go. Yes. Great. So, guys, thank you very much for the introduction, and to everyone else out there, good evening, good afternoon, or good morning, and welcome to the last GroupBy presentation of 2017. And well, what a privilege it is to be here sharing this little bit of time with all of you out there. So, as it says on the slide, my name is Gavin Campbell, and that's my website at the bottom there, arapimer.uk, and we're going to be spending the next 45 minutes or hour or so talking about effective unit testing for SQL Server. If you want to get in touch after the talk, this is probably the best way. I kind of do Twitter, I do the SQL Slack community, but the only thing that really has an SLA is email or its equivalent, like filling in this page on the website. So a bit about this talk. As you can see from here, I do quite a few different things at the day job. And whilst I'm talking about how we write unit tests, obviously that fits into this much bigger picture about continuous integration and continuous delivery and all of that good stuff, even the dreaded DevOps. So whilst I don't really have any presentation stuff about that, I think comments and questions about all that stuff are definitely very much on topic in the Slack channel or afterwards, because it would be foolish to pretend that this testing thing kind of exists in isolation. Also here on the site, there is a list of talks that I've done, and here is GroupBy here, and if I click on this link, that's a link to a hosted version of the presentation that's the same as this one I'm reading from. I'm not going to click on it now to avoid any kind of presentation inception. So having said all of that, why are we here? What's so great about unit testing anyway? Well, it might be sensible to start by considering what do we mean by this thing called unit testing? And what do we mean by this thing that we call a unit? Well, there's one definition that I kind of like, right? And it came from Microsoft's website, and it reads like this. The primary goal of unit testing is to take the smallest piece of testable software in the application. Now, it's possible to get really bogged down in thinking about what do we mean by a unit when we do unit testing. And I heard this story once, or it was on a website, on Martin Fowler's website, about a guy that had been to a course about testing, and before lunch on the first day, the instructor had something like 25 or 30 or some ridiculous number of definitions of what a unit was. But I think the real takeaway is that it's actually not really important what the unit is. The unit is a small thing that you can test independently. We isolate this unit from the rest of the code. Isolation is really important because that's what guarantees that we're only testing the thing that we actually intended to test, and we're not accidentally testing a load of other stuff that we don't really care about in the context of our unit test. And finally, we determine whether this piece of code, the unit, behaves exactly as we expect. This is important too, because this helps us draw a distinction between, so there's all this stuff that our code is supposed to do, like do the things it says in the spec or run in a reasonably fast manner. But all of that is not really our concern here, right? This is about this piece of code here that we're inspecting or writing code to inspect. Does it do what we thought it was going to do when we wrote it? So this is what unit testing is all about. So this is actually from the Visual Studio 2003 documentation. The Visual Studio 2017 documentation is much less concise on this particular point, but you can still download the old docs from that link there in the slide. So what makes a good unit test? Well, there's a couple of things. We want our unit tests to be fast. This is because we want to be able to run them over and over again. We want to be able to run them on the developer's desktop. We want to be able to run them when we check in or push or merge our code with the other developer's code. We want to be able to run them on a CI server. And because we want to do this so often, we want all of our unit tests to be able to run very quickly. Secondly, we want our unit tests to be independent. This is independent of one another. So this thing about having a coded test that depends on the value of another coded test, that kind of crops up sometimes in like a UI testing type scenario, but really that doesn't concern us here at the unit testing level. We want our test to be reliable, and I kind of have a special technical meaning for reliable, where reliable is the opposite of fragile. So a test that is fragile is a test that can fail for some reason other than the code that you're testing is wrong. So that can be something like it depends on some external service that's absent. It depends on like a user doing something. We want our test to be reliable so that if our test fails, we know that we have to go and fix something. We don't go and have to go looking around for other causes. And finally, kind of an extension of that, we want our test to be specific. By specific, we mean really we want each test to test only one thing. Yeah? That means that we know if our test for that one thing fails, we need to go and fix that one thing. If we have a test that tests a bunch of things, then we have to go and consider, well, which of those things do we need to go and test first? We'll go and investigate first. So we want our tests to be as specific as possible. So all this fits into this notion of a test pyramid. This is originally from a book about agile software, but there are a few different versions of it on the internet, most of them drawn slightly better than this. And what this is intended to illustrate is either depending on your interpretation, either the number of tests or the amount of effort that we put into each of these types of testing. And I think Google did some work on this on their own internal projects and figured out that they wanted the base of the triangle, the unit tests, to be 70% of their effort in testing. The integration tests to be 20, and these acceptance tests only to be 10. So why is that? Why do we want to have so much more effort expended on unit tests? Well, this speaks to the characteristics of unit testing. As we move up the pyramid, the tests at the bottom are very fast, and we want to be able to run them over and over again. As soon as we get into integration testing, and it doesn't matter how we define these terms precisely, integration testing, we're incorporating some external dependencies, some code that we didn't write, maybe a file server. All that stuff makes our tests slower. Finally, the acceptance tests. Well, these are generally concerned with driving of the UI, or even getting a human user tester to drive the UI. And obviously, all of that stuff takes forever compared to running our short, specific unit tests. Also, as we move up the pyramid, we go from reliable, where if a unit test fails, we know we have to go and fix the thing that it was testing. But an integration test is, by definition, more fragile. The FTP server might be down. We might have some problem with Active Directory. All of those things, some external service we depend on is absent. And at the top of the tree, well, acceptance testing in any software system tends to involve a couple of things, right? It tends to involve browser automation, which is like a nightmare for things failing for reasons that are nothing to do with your code. And browser not automation, where there's a human driving the browser. And there are many things that can go wrong there that can cause your test to be marked as a failure that don't really have anything to do with the code that you wrote. Another way I kind of like to think about this is in terms of this notion here. And this is something called the circles of influence and the circles of concern. And you know what, I had no idea where this was from, right? But so I ended up searching for it. It turns out to be from this book called The 7 Habits of Highly Effective People. Right? It just shows how much that stuff penetrates our culture. Right? So anyway, the kind of idea with this picture here is that the stuff in the light circle in the center, which is our code and our tests, are the only things that we're actually empowered to fix. Yeah? And all these other things in the blue circle, the circle of concern, are kind of all the things that can go wrong. Yeah? Right. And so the idea in this chapter of the book is that effective people, and in our case, effective developers, try to maximize the size of this circle of influence, the things we can actually fix, compared to the things we have no control over. So these are things like the behavior of the users, the behavior of the SQL server, the performance, the volume of transactions, third-party services. All these are things that if we worry about them, makes us less effective at writing our code, because we can't really do anything about those things. Yeah, the things we can fix is the code that we're writing and the tests that we're writing to exercise it. So how this fits into the pyramid model is that at the base of the pyramid, the size of the circle of influence is indeed maximized relative to the size of this circle of concern, right? All the things in our unit tests tend to be things that we can fix. As we move up the pyramid, there are loads of things coming into our tests that we don't really have any control over. Third-party services, browsers, and even users at the top of the pyramid. So the effective tester is going to be concentrating their effort at the base of this pyramid where they have the most impact and the most control over their environment. So what does a test look like? Well, I've written a short procedure that we can write a test for. This is the Chinook database. It was on Codeplex. I think there's a version on GitHub. And it's kind of like an iTunes database where you can buy tracks and albums and all the rest of it. So this procedure is called add track to album, and it kind of does what it says. It adds a track to an album. It takes 2 parameters, both int, and sets the album ID of the track in the table. So how do we go about writing a test for something like this? Well, everyone's written scripts like this, right? This is how you write a stored procedure, and you think, right, I'm going to see if that works. Yeah? So what we do is we set up a bit of test data, and then we run the procedure to see if it, see if it runs without, crashing or throwing an exception. And then we do a select at the end to see what it did. Yeah? And everyone has written scripts like this. Right? And so this is kind of what a test looks like. And even this, let's say, naive example has a bit of internal structure. So it's broken down into 3 distinct phases. The first one is here, where we're setting up the test data that we need to run our test. And in this example, we set up all the data we need in all 3 tables involved in the test. In testing speak, we call this the arrange phase of the test. Next, we do the thing that does the thing that we wanted to test. This is called the act. Yeah, this is where we call the procedure or call the function or call the method that we're actually testing. And finally, we have the assert. So assert is where we say, this is what I was expecting that code to do when I ran it. Yeah. So this arrange, act, assert thing is going to come back again and again. And I've added it in the comments here. And I think when you're writing unit tests in real life, do you always have those comments? No. Right. But I think the rule of thumb is, even if those comments aren't there, you should be able to see where they would be if they were there. Yeah? You want the test structured in such a way that you can look at it and see, right, here's the setup phase, the arrange, here's the act where we do the thing, and here's the assert where we make sure we did the right thing. So having gone to the effort of typing all that in, what do we then do with it? Well, we save it in a file, right? And I'm sure this is a familiar sight to many people, right? The SQL Server Management Studio, My Documents. Right, but sometimes I wonder, right? Could you be dead clever and write some PowerShell script that parsed all this stuff here and went back and replayed it? Right, we're not doing that today. Right? The point about this presentation is that we can leverage that effort we've gone to type in that test and save it in a file, and then look for it again next time with a testing framework that's going to let us take that same effort but convert it into a test that can be automated and can be run again and again repeatedly and in a consistent fashion. So if you're writing a testing framework, you need to be implementing these things here. All testing frameworks provide these tools for creating tests. Attributes, which are ways of saying oh yeah, this is a test. And assertions, which are ways of saying, right, this is what I expect to happen. There are tools for running tests. These can be graphical test runners that run maybe in an IDE, right, or in their own GUI, or command line test runners, which are obviously for these CI/CD scenarios where we run stuff from the server. And finally, there are tools for parsing the output. They can be machine readable for use in CI and CD servers or build servers, or human readable. That might be some visual thing in an IDE. It might be something on a dashboard. So if you're inspired to go away and write your own test framework, if you don't implement kind of these 3 things, your buddies at the golf club who are writing their own frameworks are going to be laughing about your framework when you're not around. So there have been a whole load of these written over the years. And it kind of started, certainly this type of test framework, with something called SUnit, which was a test framework for a language called Smalltalk. Now, Smalltalk, I guess, never really took off in the way that it was envisaged back in the day. And JUnit soon came along, which was a test framework for Java that implemented much of the same things. After that, there was early NUnit, a test framework for .NET. And then starting in 2005, Microsoft had a reinterpretation of what NUnit had done, and that was called MS Test and shipped with Visual Studio back then. So out of NUnit, there was also a framework called tSQLt that was a load of stored procedures that could help with test automation. And finally, out of the 2 of those, the framework we're talking about today called tSQLt. Now, before I move on from this slide, there is something to call out. You'll notice that these test frameworks kind of map one-to-one with the language or with the framework that they're intended to test. Yeah? And there's a reason for that. We want the developers to be able to use the same tools and environments that they use for writing the code to write the tests. Yeah, this is all about reducing that context shift between, it's kind of less useful to be saying, oh yeah, so I'm going to write a load of stored procedures in my application here, and then I'm going to change to, let's say, Visual Studio or something, and write a load of tests in NUnit over here for my SQL Server to code. So that thing about having the same language for the tests that we have for the code, it's about context switching and maybe to a lesser extent about skills. Like you might necessarily not want to learn another language, e.g. Ruby, to write the tests for your .NET or SQL Server application. So tSQLt, you can download from this website here, tSQLt.org, and I'm just going to scroll a little bit so we can see some features. So what does tSQLt do? It's a unit testing framework with SQL Server. compatible with SQL Server 2005 and onwards. Every test is automatically run in a transaction. Now this is actually a good feature, and most, I guess, OO frameworks can't do this, right? Like it creates a transaction at the start of a test, does the test, and then rolls it back at the end. So that means whatever happens in the test, the state of the database is the same at the end as it was at the start. Yeah? And that's really powerful because it means that all the tests can be independent of one another and can be run in any order. Output can be generated as text or as XML. Well, that's like the human readable and the machine readable versions of the output. And it provides the ability to fake tables and views. This is the really important feature. In fact, like if it wasn't for this, I think tSQLt would be not interesting at all, right? And we're going to have quite a few examples of that further down. So in terms of ticking off the list, tSQLt has tools for creating tests, which are test classes. This is a way of saying, yeah, this thing here is a test. It's not really part of my application. It has assertions. This is what I expect to happen. It has tools for running tests, which are all stored procedures. tSQLt.run, tSQLt.run test class, and there are others for running different subsets of the tests you have. Yeah. There are tools for parsing output, either as text or as XML for consumption by a build server. But it does more than that. And tools for isolating dependencies. Now, if you've done unit testing in other languages, let's say with .NET testing frameworks, you kind of have two decisions to make. Let's say you've decided you're going to use NUnit or XUnit or whatever to do your tests. We have this other thing. How are we going to do mocks? How are we going to do fakes? Yeah. So then we have this other discussion about, are we going to use nsub? We're going to use mock. And there are others, the Microsoft one, moles. Yeah? But here with tSQLt, all that stuff is kind of in the can, right? So with tSQLt, you get the test runners and the output formatters, but also you get all the mocking tools built in that can mock objects in SQL Server, as the name suggests. So when you download tSQLt, you end up with this SQL script here. Right? Where you run this is in the database that contains the objects you're going to test. So this has a couple of implications, right? The first is you're not doing this in production. Yeah? Right? This is in some other environment where it doesn't matter what you do with the objects in the database. Yeah? Right. The second thing is, you can see further down in this script, this requires CLR to be enabled for the server. Yeah? Now, I'm not one of these people that subscribes kind of the conspiracy that enabling CLR is going to cause your server to be taken over by man hackers at any moment. Right? But having CLR enabled is let's say, a code smell, isn't it, in any SQL Server application. Yeah? And often what CLR enabled means is this application is doing something that it shouldn't be doing in SQL Server. It should be doing it somewhere else in the application stack. And that indeed is true of tSQLt. If you think about what you have to do to write a test framework, there's lots of non-databasey, non-set oriented stuff you have to be able to do. Right? You have to be able to do iteration over these collections of tests. Right? You have to be able to run them one after the other. You have to do all this text processing stuff, which again is no fun at all in tSQL. So kind of that's why tSQLt has this requirement for CLR to be enabled. It's because it needs that to do some stuff in kind of a convenient way that would just be acres of code in tSQL to do. So when you run this script, kind of this happens. Thank you for using tSQLt. If that doesn't happen, I guess it's back to the website to read the instructions again. Yeah? Right. Like any framework, tSQLt has a couple of rules, and there aren't many. So in tSQLt, a test class is a SQL Server schema that has some extra extended properties. And it can be created with this stored procedure called tSQLt.newTestClass. It can also be created with createSchema, but then you have to know what the extended properties are that you need and know how to set those manually. Right? And there are some scenarios for doing that. The second thing is a test case or a text fixture is just a stored procedure that belongs to one of these schemas that's been identified as being a test class. And the name of the stored procedure has to start with the word test. And that's about it. Those are all the rules, right? The reason that the stored procedure has to start with the word test is that in other languages we have these things called attributes that enable us to tell that yeah, this here is a test. SQL Server has no equivalent. There's no way of decorating a stored procedure to say, oh yeah, this one's just a test. So it has to go in the name. So if we revisit our earlier test written for tSQLt, we can see that the arrange, the act, and the assert are all still present and identifiable, but not commented. But there's some extra stuff here that we'll step into. So first we say, create a new test class, and the class name is add track to album. This is kind of significant actually. Right? The name of the test class is the name of the stored procedure that we're creating. Yeah? And it's going to create a schema with that name. And this is kind of a weird thing for SQL Server people, because then it's like, oh, doesn't that mean that we're going to end up with like hundreds and hundreds of schemas in our database, like one per stored procedure that we're writing tests for? And the answer to that is yes, right? Like, and the reason for that is that this schema mechanism is being hijacked to do something else, because we have no way of implementing like class in tSQL. We create it with the same name as the stored procedure, so that we keep all the stored procedures, all the tests that go with this stored procedure together in the same schema. And for instance, they can all be run together independently of the test for some other procedure. Then we go on to creating the test itself, and this is just a stored procedure. So we create procedure in that schema, add track to album, test, which is required. Existing track added to existing album succeeds. Now the name is kind of important here, right? We're saying the name of the thing we're testing, add track to album. That's why we use that as the schema name. The conditions in which we're testing it, existing track added to existing album, and what we expect to happen. And all of that is in the name of the test, right? Like, at the start, we're starting the arrange phase. So we do fake table a couple of times. Fake table is the real like big win with tSQLt. So what this is going to do is rename the existing DBO album table to something else and create a new table called dbo.album that is empty, has the same columns, the same column names, the same column types as everything in the real DBO album table, but with no constraints. Everything is going to be nullable. There are going to be no primary keys, no foreign keys, no check constraints, defaults, identities, all that stuff. And what that means is that when we're setting up our test data, we only need to insert the columns that we care about in the context of this test. Yeah? So all the other ones that are needed to satisfy, let's say, foreign key constraints, like the old test even had setting up stuff in artist, because that was a foreign key to track. But now we don't care about that, right? All we're actually interested in is what does this stored procedure do? So this is isolating this stored procedure from its dependencies by saying, yeah, don't use the real tables. We're just going to use these fake ones instead. So we've set up our data. Now in the act, we call the stored procedure. And now we move on to the assert. Now we have a bit of setup to do here. We're using select into to create some new tables in the database. Huh? All right, we're going to select the two things we're expecting, the album ID and the track ID, into a table that's called expected. And that's kind of a permanent table. And then we're going to have a look in the track table that that procedure was supposed to update, which is just a fake. And we'll select that into a table called actual. Those names are not important, actually. It's just that's kind of a convention that I use and is suggested by the IntelliSense for tSQLt. Right, and then finally, we do the assert. So we're saying, having done all that, the expected table that I've defined should be the same as my actual table, meaning those two values should have been inserted into the table. And then when we run that, we don't run the stored procedure directly, so I've got ahead of myself. We never run the stored procedure directly. All that stuff I talked about with transactions isn't in here. Yeah. So the beginning of a transaction at the beginning and rolling back at the end is handled in the test runner. So when we call tSQLt run all or tSQLt run some other subset, that's what's going to take care of begin transaction at the end, begin transaction at the beginning and throw away the transaction at the end. So we don't need to worry about all those changes we've made to the database in the scope of the test. They're all going to go away at the end. So when we run the test, something like this should happen. And it says, we've run one test. We've tested that adding an existing track to an existing album succeeded, and it passed. Now, we're often told that in test-driven development, or whatever, we should be writing failing tests. Yeah? And the way we make a test fail is by making a change in the code we're testing. Yeah. So we're going to say, right, instead of setting the parameter, instead of using the parameter we've passed in to set this album ID, we're just going to set it to null. And this is going to make our test fail. And indeed, when we run the test, that's what happens, right? So it's telling us here, it was expecting a 456 and a 345 for album ID and track, but actually it got a null. Yeah. This is kind of important. To generate a failing test, we didn't change the test to make it fail. We changed the code we were testing so that the test failed for the right reason. Imagine things have been a little different, and that procedure actually had a bug in it. Yeah. So instead of using the album ID we passed, it had like an off by one error, and it was inserting one more than that. But we didn't bother to change the code. We decided, right, we're just going to decide to make a change in a test, so we're going to expect the wrong thing. We're going to expect a null. Yeah. And indeed, that test is going to fail. But it would fail whether or not the bug in the procedure was present. Yeah. So by doctoring our expectations in the test, we're making our test fail for the wrong reason, and it's not helping us to identify like the fault in the procedure. So the takeaway is, when adding tests to legacy code, we change the code and not the tests to generate failures. Now, there's another feature here in tSQLt, and this is a feature that loads of test frameworks have, these custom assertion methods. So we can say exec assert equals table between the expected and the actual, and if it fails, give me this message, failed to add track to existing album. So when we run that, we get a failure message, and it says add track to album, test existing track added to existing album succeeds, failed, because failed to add track to existing album. So what's wrong with that? Right? Like, what's wrong with that is the message isn't telling us anything that isn't in the name of the test. Yeah? And it's because we chose this sensible name for the test that we don't actually care about custom failure messages. So the way we name our tests is the name of the thing we're testing. That's the name of the schema. What we did, what the initial setup was, and what we expected to happen. Yeah? That seems like a silly thing, but it's really important. It's on a post-it note here, right? Stuck to my monitor. And not really, I don't forget that when I'm doing tSQLt tests. I do forget that when I'm doing tests in other languages, to get that correctly structured, the thing we were testing, the conditions we were testing it in, and what we expected to happen. So in general, if you find yourself reaching for custom error messages, you should probably have another look at the name of the tests that you have. Let's move on to another feature. So this is a table valued function. And so this selects some stuff from a few tables, joins it together, and returns a table. It's the list of all tracks purchased by a customer. And the reason I have this example is to demonstrate a pattern or a heuristic that we kind of use for testing data-intensive things. And this is known as testing not one or an n, or not one and many. So what the idea here is that we're going to write a set of 3 tests for this stored procedure. One in which it won't have any rows to act on, one in which it will have 1 row to act on, and one in which will have many, or in this case 2, the important thing is more than 1, rows to act on. And those are going to enable us to drive out different aspects of the behavior of this function. So this is the first test here, and this is the 0 case. Yeah? So the test is called get tracks purchased by customer, test no purchases, returns an empty result set. So you can see here we're setting up an invoice with a customer ID, and that's not the same as the customer ID that we're passing to the test, right? So the customer ID we're passing to the test doesn't have any purchases. There's a different type of assertion here. There are loads of them in tSQLt. You can go and look them up. So we don't need to bother setting up expected and actual. We can just, or expected, we can just say, yeah, we expect the actual results to be empty. Yeah. And this may seem like kind of a pointless test. Yeah. What this is actually testing is the error handling in our function. Yeah. So what we're saying here is when we call this function get tracks purchased by customers and there are no rows, what we expect to get back is an empty table. Yeah. What we don't expect to get back is like an exception, right? Or something like that. Yeah. So the 0 case is how you find out like the gaps in your error handling. After that is the 1 case. So this is a single purchase. This is really the happy path. It's the easiest test to write. Yeah. So this is where we set up a single purchase of a single track by this customer. And we're expecting to get just 1 track back for this customer when we select from the table value function. So here we're back to assert equals table, the expected and the actual. So this is, often the first test we write, right? Because it's the easiest. Yeah? Right. It's like we're going to bung 1 row into every table, run the function and see what we get. Finally, the many case. Get tracks purchased by customer, test separate purchases, return separate rows. And there's a bit more setup here. Right? So we have 2 different tracks that have been purchased. I think they're on 2 different invoices, but they're for the same customer, and that's the customer we're passing to the function. And when we run the test, we expect to get back 2 rows from the table valued function. Now, why is this important? Right? Now, this is kind of a simple example, but imagine there were a multi-column join involved in that query. Yeah. And in the test, you've missed off a join criteria. Yeah. So what happens in those scenarios, in a complicated stored procedure, is you end up multiplying the number of rows in the output. You end up with an accidental Cartesian join or something like it. And if you only ever test with one row in each of the tables, you never see those, because 1 times 1 times 1 is 1. Yeah. So this is how you find, this type of test here is how you find missing join conditions, often in these like reporting type of functions and stored procedures. But there is something here, right? So there's quite a bit of repetitive code in these tests, right? We're setting up the same stuff at the start of all of them. And we can imagine if this was more complex, the amount of this setup would grow when we'd be copying and pasting it between tests. So is there another way? Well, yes, there is. And in tSQLt, there's this feature called test setup. And again, a lot of test frameworks have this, especially older ones, and I'll come to that. So there are some extra rules for test setup. It has to be in the schema where the tests are, so that has to be a test class, and it has to be called setup. What tSQLt will do with this is at the start of every test in this schema, get tracks purchased by customer, it will begin the transaction, call this setup procedure, then do the test, and then roll everything back. So that means that in every test in this test class or in this schema, we know that all this stuff here is already going to have happened before we get into our test code. Right? So we abstract that common code into this setup procedure. So we fake those 3 tables, and we set up, let's say, 3 rows of test data that we can use for like a whole bunch of different tests that we might want to write. Yeah? So what does the test look like now? So we're creating the procedure. This is the separate rows case. Right. So we've got act. We're going to call this function. This is what we're expecting to happen. Yeah. But there's something missing, right? There's no arrange. Yeah? Right. And that's because arrange has been like hidden in that other procedure. And that test setup business, that's a feature from like old NUnit really. Yeah. Right. And even the founder or inventor or whatever of NUnit, I think, has said not that long after inventing NUnit that if he was doing it again, there'd be no common setup routines. Yeah? And the reason for this is that the price you pay in, let's say, diminishing the readability or the comprehensibility of this test isn't worth the convenience of having that stuff hidden in another method. This is context switching again, right? So if I look at this test and want to figure out, oh yeah, what does that do? Well, then I have to go and, find the other file, right? And say, oh yeah, so here's the test setup here. And now I have to have 2 windows so I can see the rows that we're setting up and what we're doing in the test. Fortunately, there's another way. We're going to create some helper procedures. So again, I'm going to put these in the same schema as the tests, but that doesn't matter really. I just kind of put them there because they kind of go with these tests. Yeah. So in this schema, but the name doesn't start with the word test. That means that the test framework isn't going to detect it and automatically run it. And the procedure is called fake track invoice and invoice line. It has a long name that says what it does. And it does just that. Fakes those 3 tables, and we're ready for then we're ready to insert the data. That's done by a longer procedure called a test data builder. So again, I've used the same naming convention. It's in the same schema as the tests, but it has a name that doesn't start with test, so we're going to have to call this manually. Yeah? Test data builders are characterized by having a whole load of optional parameters. What we can do with these optional what we do with these optional parameters is we define one for every column of every table we're interested in for this test. Yeah? All of them are optional because they all have a default, and the default is always null. Yeah? There's a bonus example here of how to use an output parameter in a test data builder. So this is maybe in real life that's done by a sequence or by an identity, and we just want to make sure that the calling code knows that it can never know ahead of time what that value is. Yeah. Like that's going to come from like scope identity or something in the real application. Sorry, there we are, setting it to a random value. So because we've set defaults of null to every single one of those, when we actually insert the data into the faked tables, almost every column will be inserted as null because we haven't passed it in a call to a stored procedure. But that's fine. We can pass only the parameters we care about for the scope of this test. Yeah? That's kind of abstract. I have an example of using it. So here, we have a revised test using this test data builder. And instead of all that setup stuff, we're just going to call our 2 helper procs. But now you can see what this test does, right? Now it says at the start of the test, we're going to fake those 3 tables. And then we're going to do this thing create an invoice for one track, and we can see in the test what the data was we were passing in. Yeah. Now there's a whole lot of other parameters to that create invoice for one track procedure, but we don't need to care about them. They're just going to be inserted as null, and they're not relevant to our test. Yeah. Finally, the rest of the test is just the same, but we can see from this test that when we set up a track like that on its invoice, at the end, that's what we expect to get back from calling the procedure. So there we use helper procedures and data builders, not setup procedures. I have a couple more examples to go here. So this is maybe a common scenario. This is playlist to track in our iTunes-like database. So this is a many-to-many table with 2 foreign keys. And we also have a datetime2 column that we're going to use to log whenever we make updates or inserts to this table. Right? This is a fairly common kind of thing. Then we have a procedure that merges into this table and so puts in the 2 values that we've passed and sets the column to sysutc datetime, which is the millennial get date. Right? So here, when we write a test, we're saying test that a valid track in a playlist was inserted, but what are we expecting? Yeah? When we select from that playlist track table, well, we're expecting our 2 keys that we passed in to come back, 66 and 67. But what date are we expecting? Yeah, well, we don't know, yeah? Like, because we were calling sysutc datetime inside the procedure to give us a date to put into the table. So how do we go about writing a test for something like this? Right, method 1, right, widely used, including by me, because sometimes method 1 is the only method. Yeah, right. In the test, we cast what we get. We cast the current date as a date, yeah, and we store that in the expected table. Then when we select from the table that was acted on by the procedure, we cast that to date as well, yeah. So that means that it's kind of safe to compare the date that we're expecting, the date portion of the date we're expecting, with the date portion that we inserted, yeah. And yeah, this is kind of okay. So it's obvious when this is going to fail, right? It's going to fail if the 2 bits of that test happen at either side of midnight. Yeah, and that's normally all right. Yeah, but this test is more fragile, right? Because we've introduced a reason that this test can fail that isn't because there's something wrong with the code. Yeah. So is there another way? Well, yes, but it involves changing the code itself. Yeah. This is a really common thing to do. I've done this week at work. Right. Instead of like casting the results to date, yeah, we're adding an optional parameter to the test. Yeah? And that means that current users of this stored procedure don't need to know about my optional parameter datetime2. It's just going to be passed as null. If it is passed as null, we'll just set it to the current date and time. So that means that for existing clients, it will just work. Yeah. So finally, when we do the thing, when we do the merge, we don't call sysutc datetime twice. We just insert the contents of that variable. Yeah. Now, what that means is that when we write the test, or we can create our own time and date outside of the test and pass that into the procedure when we call it, and that gives us a predictable result that will work, including at midnight. This test will pass as long as everything in the code is all right. Yeah. So this technique kind of has a name, right? Like so in .NET land, this is called dependency injection. Yeah. So this is where instead of like letting the code go away and find all the things it needs to do its thing, including the time. And time is so often the problem, yeah, that it's more like we tell you what time it is, and then we're going to see what you do based on that information. Yeah. So here, yeah, when you can, it's okay to change the code to make it easier to test. Yeah. And one of the ways we do this is this like fake dependency injection by passing dependencies as optional parameters wherever we can. Right, in this next example, I kind of have a strict rule about like not stealing stuff from clients to put in public presentations, right? But this line here, right? I think if the client's watching, they know who they are, right? So this is a stored procedure that runs every night to perform various tasks, yeah? Right? And yeah, I have seen that comment, and this is not so uncommon a thing, right? A stored procedure that does like everything, yeah, that runs on some schedule, and I think if I scroll a bit, we can see some of the stuff, right? Like, so if it's Monday, it does this thing in the genres table. On Wednesdays, it does something to tracks. On Thursdays, it updates some derived measure. on Friday we send a birthday email to every employee whose birthday is the next week, and you get the idea, right? And yeah, this is far less uncommon than you might think. So where do you start, right, with running a test like this? Well, we know about isolating dependencies, so we had a bunch of mocks. Yeah. Now actually this list is kind of tame. There are what, 7 or 8 in there. Yeah. You can easily imagine in like your own company's version of that epic procedure, there could be like 20 tables, some functions, some views, some procedures, and all those things have to be mocked before you can write a test for do all the things. Yeah? And that itself is a code smell, right? This is testing telling you something about your code. Yeah? If you have to mock like the whole universe to be able to write a test for your procedure, this is the sign that there's something wrong with the procedure. It's doing too much. Yeah. So again, where we can, we refactor the procedure. Yeah. And what we do is we make it more modular, right? So we encapsulate all those things that it does on the various days of the week into these independent store procedures, which we can then fake when we're testing the outer procedure. Yeah. So in the context of testing do all the things, we don't really care what those inner procedures do. We're just going to fake them, and we can create specific tests like this one. Yeah. So we can say do all the things. On Thursday we update artist rankings, but in the context of testing the outer procedure, the mega proc, we don't care about what that does. Yeah. We're going to use spy procedure to create a fake of it, which is a copy of the store procedure that doesn't do anything except to log that it was called and with what parameters. Yeah? So now, when we say, right, we're going to call that store procedure and pass it Thursday, the only thing we're going to test is, oh yeah, so on Thursdays we called that procedure called update artist rankings. We don't care about anything else. Yeah? We can do negative tests like this too, right? So we can say on Thursday we don't do update the postcodes. So we create a spy of the procedure, and we call do all the things. Again, we look in this table, update missing postcodes _ spy procedure log. So that was created by spy procedure, and that's going to record one line for every time we hit that procedure, for every execution. Yeah. And that row will contain like an ID, and it will contain whatever parameters got passed. In this case, there aren't any. So we only care about the count. So having got started with that, we can save loads of time by testing more than one thing at once. Yeah. So here's a test. On Mondays, we delete the empty genres and update the artist rankings, but don't increase prices or update missing postcodes. Yeah. Great. Yeah. We can test all that stuff at once. Right? But there are a couple of alarm bells here. Yeah. And you know what they are, right? They're in the name of the test. Yeah. So here, there are some conjunctions. Yeah. The name of this test has an and a but in it. Yeah. So almost like by definition, we don't even have to look to see that there are 4 asserts. Yeah. We can tell from the name of the test that something's amiss here. Yeah. And indeed there is. So what's really the problem with doing this kind of thing, right? Well, we're going to run this test. Yeah. And imagine, passes, great. Yeah. So imagine now it fails, right? So then we see in our report of tests, oh yeah, this test that tests on Mondays we delete empty genres and update artist rankings but don't increase prices or update missing postcodes. That's failed. Yeah. Well, good. So which one of those things didn't it do? Yeah. Which one of those things made it fail? So that's kind of why we try to keep our tests down to like 1 assertion per test. And this isn't the answer either. Yeah. So we can convert our 4 assertions into like a compound assertion. Yeah. To say, oh yeah, like on Monday, all of those things happen. Right. But yeah, this is also not really the way ahead. Right. The way ahead is with 1 assertion per test. Some things we can't mock. This is a system stored procedure, but that's not the reason we can't mock it. It can't be mocked because it's in a different database, and tSQLt can only act on the things that are in the same database where it is. Yeah. So this is XP log event, a system thing, but it would equally apply to something you're calling through a link server or something like that. Yeah. So instead of mocking it, we wrap it. So we create our own procedure called do pointless logging that does the pointless logging. Yeah. Right. And you can probably use this in 100 different applications afterwards, couldn't you? Right. And then we can write a test that says, on Thursday, we don't do pointless logging. Yeah? So now, because we've got a procedure that we own, we can create a spy for it. Yeah. And say, mock this procedure, do pointless logging, call, do all the things, and assert that on Thursday we didn't hit that procedure because we only do pointless logging on Fridays. So the takeaways here, mocking the whole world is a sign that the procedure is doing too much. And if you have difficulty saying what the test condition is, you're going to have difficulty maintaining it. Yeah? Right. Final set of examples are about exceptions. Always a fun topic. So here we have a stored procedure that adds an invoice line to an existing invoice. Kind of a common thing to do. Right? take some parameters. Those are all the columns from the invoice line table, except for the key. Let's just imagine that's an identity. And we're going to insert those values into the invoice line table. So obviously, there's a foreign key between invoice line and invoice. That's kind of implicit here. Yeah. So as well, let's write a test for that. Yeah. So we're going to say create a test, add line to existing invoice for this procedure. Test the non-existent invoice throws an exception. So right, we're going to fake all our tables, invoice and invoice line. But here's another feature of tSQLt, apply constraint. Yeah. So having made a fake copy of invoice line, we can say, no, not completely fake. I want to bring back this one constraint, yeah, this foreign key from invoice line to invoice. Yeah? So now we have kind of a partial, there's still no data, but now there's a constraint between that and the invoice table. And now we can say tSQLt, expect exception. So what we're saying here is when I run line after this, or a line after this, I'm expecting an exception to be thrown, right? And we're expecting an exception to be thrown because that foreign key is going to be violated. The invoice table is empty. So anything we insert into invoice line is not going to match it. Yeah? And this test passes, great. Yeah? So what have we just tested? Yeah? We've just tested that foreign key works. Yeah? Right. Now foreign key has been in SQL Server since version 6. Yeah? And we kind of hope that Microsoft already have some tests for whether or not foreign key works. Yeah? And often, like, if you're using these additional features, there are scenarios for them, right? In particular triggers, right? Like where we want to fake a table and then bring back a trigger to say just test the stuff in that trigger. Yeah. Obviously, the end goal is getting rid of the trigger, right? But maybe one of the steps towards that goal is having some tests for it. Right? So there are some scenarios for bringing back constraints, but it's easy to stray into testing things that you're kind of hoping Microsoft already tested when you're doing that kind of thing. Yeah? Right? So a slightly better example of this is this. So this is certainly an older code. You see this kind of error handling, don't you? Right? We've got a procedure that takes a parameter, yeah, and it's going to validate that, you know, that parameter matches something in the other table. And if it doesn't, it's going to call a procedure called log error that's going to log an error, and it's going to throw an exception. Yeah, right. But if none of that happens and the artist ID is valid, then it's going to insert the data into the table. So we can use that expect exception to test this procedure as well. So here, we're going to test that a missing artist throws an exception and writes a log record. Yeah? So we, again, we isolate our dependencies. We call fake table a couple of times. We fake out that log error stored procedure as well. And we say, right, expect an exception. Something after this is going to throw an exception. Yeah, right. And then also we're testing the logging. So we're going to set up our log message into this expected table and use assert equals table to compare that to the actual that we select from the SPY procedure log. Yeah? So this test is going to pass, right? This test is going to pass too. Yeah? It actually doesn't matter what we put into the expected for the log message. The test is going to pass every time, and that's because of expect exception. Yeah. And when we say expect exception after this, we're kind of telling tSQLt, get ready, we're about to throw an exception. Yeah. Right. This line here, the store procedure call, is what throws the exception, and then it gets caught, and nothing below that ever gets hit. Yeah. So this test is going to pass every time, but we're never testing that the logging thing actually happens. We're only testing that the exception gets thrown. Yeah. But there was actually a clue in the name, right? There's a conjunction in the name of the test. Yeah. Right. The name of the test is test that this procedure here in this error condition throws an exception and writes something to the log. Yeah. This is the thing with exceptions, isn't it? Really. So you can have a function or a method or something that returns some value, but that's not really the whole signature of the procedure. It could be. This stored procedure will, return some value or produce this result set, or it might throw an exception. Yeah. So that's kind of some implicit additional piece of information about the procedure that is kind of difficult to see when you just type create procedure. So the answer is that we create a separate test. Those are really two separate assertions. They're two separate things the procedure can do. It can write a message or it can throw an exception. Yeah. So to test writing the message, we need to catch that exception ourselves. This is a good tSQLt top tip here. Right? So we're going to call the store procedure, but we're going to do that in our own try-catch block. But our catch block doesn't do anything. All it does is stop the exception from being surfaced back to the calling code. Yeah? That means the exception is caught, and we're free to go and inspect what's in the log table to make sure it's what we're expecting. Then separately to that, yes, we can have a test that it throws an exception, and there's no and whenever there's test anymore. Yeah. All we have to do is set up our fakes, call the procedure, and say, yeah, we've got an exception, and the test is going to pass. So yeah, we treat exceptions as separate tests, and also we don't really need to test that like SQL Server is working. Yeah. So in summary, arrange, act, assert, we need to be looking for that in all of the tests. We need to see that pattern in every kind of tSQLt test we write. We mock our dependencies out to isolate the code that we're trying to test. We only test the code that we own, again, coming back to that thing, right? But not just what Microsoft have written, what your third-party partners have written, really. You really want to be putting it on them to write the tests, and you just test your touch points. We change code, not tests, to generate a failure. That ensures that when we do generate a failure, we're failing for the right reason. We observe our test naming conventions, because that means when we see in our log of 500 tests that this test has failed, we can see without drilling in any further what it is we need to go and fix. We use data builders rather than setup stored procedures. We're not afraid to refactor our code to make it more modular and easier to test, or indeed to inject dependencies wherever we can. We need to be careful with exceptions, and that's about all. Thanks for listening.
Very cool. Nice session, sir. Very nice introduction to testing there. Had a nice lively discussion in Slack along the way. For example, Beats Alien was like, it's neat to have a test where you expect failures to happen, and you have to have that in order to pass the test. That's pretty cool. Where would you go to learn more about testing moving forward for the folks who want to learn more?
Right, okay, there's a couple of things there, right? So tSQLt itself is pretty well documented on the tSQLt website, right? Like all the parameters, there's a whole load of stuff I haven't shown there, yeah? And it kind of says how to use all the bits of tSQLt, yeah? I think one of the things that's lacking maybe in the SQL Server literature is like the great book about testing, yeah? What you'll find is that does exist for Java, and it does exist for C#, yeah? So actually a lot of this stuff about solid, which is what we talk about, .NET programming or in OO programming, a lot of being more effective in writing SQL Server tests is applying stuff that is good practice in other programming languages to SQL Server. Yeah. So, the original Extreme Programming book is certainly something worth looking into. Yeah. Like Michael Feather's book, Growing Object. Is that Michael Feather's? Have I just got that wrong? Growing Object-Oriented Software Guided by Tests. Who wrote that? Right,
no clue. Yeah.
No clue. So Michael Feather's book about legacy code, and where legacy code is defined as code that doesn't have tests, right? There's something to think about. Yeah.
Every piece of code I've ever written.
Yeah. So really, a lot of this stuff comes from applying things from other programming languages. Yeah? And I think there are some people who've written a few blog posts about things like Ed Elliott or Call Out. I'm not sure if he's in the chat or not. It's kind of late here in England for him. But he's often in the SQL Server Slack channel and has stuff on his side about it. I don't know if James wants to help me with any others about tSQLt. Well, Redgate have a front end for it, yeah? So possibly Redgate have some information about, and Redgate's front end is just a wrapper for calling those procs, right? So possibly Redgate will have some kind of insight in what you actually do once you're using their front end to call the procs. Yeah.
Gotcha. All right. Well, thanks a lot for giving the presentation today.